Hi everyone, this is Mrs. J, and today we're going to learn about functions, continuity, linearity, intercepts, and symmetry. So we're really starting to talk about some of the key features of functions. I have a quick warm-up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. This is just to review a couple of basic skills from Algebra 1. So the first one is substituting values and making sure you're following order of operations to help you evaluate. The second one is just solving for different variables, so isolating that variable within an equation, and whether you write your answer like this or this, they're completely equivalent. So of course, when we start talking about functions, the first thing we really need to talk about is what exactly is a function? What is that definition? So a function is a special type of relation where every input has only one output. That is the essential definition of a function, which essentially means every x value has only one y value. So this is important to us because, functions actually model real life scenarios. So this is saying that every time we plug in some input x, every single person in the entire world would get the same y value. They would get only one y value or only one output. So again, this is the definition of a function, and it's super important to keep this in mind throughout the entire year as we start learning about different types of functions. So there are two ways we can classify functions. We can call a function a one-to-one function, where in this case, every output also only has one input. So again, we already know that it's a function, but a one-to-one function, again, every output has only one input. Or we could say that it's a many-to-one function, which is a function where some outputs have multiple inputs. So just some different representations of some number relations. So in this relation here, we can see it is a function because every input has exactly one output, compared to this relation here where the input of 9 has two different outputs, which makes it not a function. But this one, again, you could see that each input has one output, and every output only has one input. But then if you look down here at this relation, it is still a function. Every input gives you exactly one output. However, you can see that this output of 4 has two different inputs, which again is fine. It still makes it a function, but we call this a many-to-one function because there are multiple inputs that give you the same output. So how can we tell graphically if something is a function? So for this, the way we test to see if every input has one output is with the vertical line test. So the vertical line test essentially says that you should be able to draw a vertical line at any point on your graph like this, and that vertical line should only cross your graph at one point. So you can see in this first example, no matter where I draw a vertical line, it only touches at one point. So that means that every x value has only one y value, which means it is a function. So yes. Now, if you look at this next example, same thing. Wherever I draw a vertical line, my graph only crosses that vertical line once, so every input has exactly one output. But if you look at this third graph, just look at right here, and this happens anything to the right of -5. If I draw a vertical line, this input, say of -2, has two different outputs. So this, because it fails the vertical line test, is not a function. Now, once we know if it's a function, how can we tell if it's a one-to-one function? So for this, we're actually going to be using the horizontal line test. So again, we're only using this if we've already determined that it is a function. So the horizontal line test, we would draw a horizontal line at any point, like here, here, or here. And if it only crosses once, then we would call it a one-to-one function. So this first graph is a one-to-one function. But if you look at our second graph, which again, we already know is a function, if you draw a vertical line, let's say here, we can see that it crosses twice. So that means that this output of -4 has two different inputs. Again, it is still a function, but we would classify this as a many-to-one function. And again, for this third one, it's not a function, so we wouldn't classify this as either, because we're only going to do that once we know it's a function. So now we're going to talk about a different way we can characterize a function, and those are with either the word discrete or continuous, or maybe we would say that it's neither. So a continuous function is simply a function, if you think about it, if you can graph it without picking up your pencil. So it's graphed with an unbroken line or curve, we would call it continuous. And then a discrete function is a discontinuous function that's just simply made up of unconnected points. And then if it's kind of neither just points or a connected curve, we would call it neither continuous nor discrete. So if you look at, let's start over here, this downward facing parabola, I see that I could draw this entire graph without picking up my pencil. So we would call this a continuous function. And if you look at this graph in the middle, it's just a series of unconnected points. So we would call this a discrete function. And you'll notice that at no point are there any connected coordinates. It's just unconnected points. Now, if you look at this first graph right here, there are portions that are continuous, but then there's a jump and then it's continuous again. So since it does have that jump, it is discontinuous and it is also not discrete. So this one we would classify as neither. And again, this is just a different way that we can characterize different types of functions. And now we're going to talk about a really important concept that we'll keep returning to over and over throughout the year, and that's domain and range. So hopefully these words sound familiar to you. We know that domain is the set of x values, or the input that is defined for any function, and the range is the set of y values, or the output that is designed for any function. Now here we're going to talk about different types of notation. I'd say as you progress through higher levels of math, we're going to kind of gravitate towards interval notation, but it is important to know how to read and write also algebraic and set builder notation. So we're going to practice all three. So you can see here on our number lines, we have 4 different relations of numbers, and we're going to talk about how to write these different scenarios using all 3 notations. So here, one thing to notice is that here we have an open coordinate at -2. Anytime you see an open coordinate or this open circle, it means that this point is not included as part of our domain or range. Here we're going to do all domains. These are x values. So it is important that we do not include -2, but everything to the right is included, and that is denoted with this little arrow. So it means that everything that is larger than -2 is included. So when you're using interval notation, we always start with the low number on the left and the highest number on the right. So you can see that our lowest number is -2, and since it's not included, we're going to be using a parenthesis. So this is called an open bracket. So we use this when the point is not, or the value is not included. And then we put a comma, and then to the right, we include our highest value. Now, if it's just continuing infinitely to the right, our highest value is considered to be infinity. And infinity always goes with a parenthesis or an open bracket. Like this, it's never technically included, and I like to think of it as, well, because it's not technically a number, so we can't technically include it. So this is how I would describe this domain in interval notation, low to high, and we can see that -2 is not included. Now, algebraically, we're essentially just going to be using inequality symbols. So here we're describing domain, so it's x, and we can see that's everything larger than -2. And then set builder notation is really a lot like algebraic notation, but with a little bit extra kind of fancy stuff going on. So here we're actually going to start with our curved bracket or a brace, and then we say what variable we're working with, so x, and then we do this vertical line. It's read x such that, and then we essentially just do our algebraic notation. X is greater than -2. So very similar to algebraic with our braces and defining the variable we're using in front. Okay, let's look at this next one. So here we can see that it's everything below and including positive 3. So with interval notation, again, it's always low to high. Since it is continuing infinitely to the left, our lowest value is negative infinity, never included. Our highest value is 3, and this one is included because it is a closed circle, so we're going to use this bracket. So this is a closed bracket, showing that 3 is part of our domain. For this one, it's everything less than or equal to 3. And then for set builder, we'll say x such that x is less than or equal to 3 with our braces. Now, if you look at this next example, we actually have a lower and upper boundary that are both defined by numbers. So our lower boundary is negative 4. And because that is included, it's a closed coordinate, we're going to do a bracket. And our upper boundary is positive 1. However, it's an open coordinate, so we're going to use a parenthesis to denote that is not part of our domain. Now, when we have something like this where it's between two numbers, we're actually going to put our x and our inequalities in the middle. So we'll still start with our lowest value, and then it's going to be greater than or equal to negative 4, but then less than positive 1. So this kind of shows that it's between negative 4 and 1. Negative 4 is included, 1 is not. Then we'll do just our extra braces, x such that negative 4 is less than or equal to x is less than 1. And then for this last one, you could see that it's just continuing infinitely to the right and left, which means it is all real numbers. So with interval notation, we'll just always say that's negative infinity to positive infinity. When it is all real numbers, with algebraic notation, we're actually going to use the all real numbers symbol. So we could say x equals all real numbers, which is that capital R with the extra vertical line. And then for set builders, we'll get a little bit fancier. We'll say x such that x is represented by all real numbers. So you can see for this one, I'm kind of using this sideways kind of E shape to denote that it is all real numbers. So these are the 3 different notations we'll be working with, and we kind of covered all the different scenarios where if points are included or not, and what to do as the values move infinitely to the right or left. All right, so now we're going to look at some different graphs and see if we can define our domain and range. We'll use interval and set builder notation. So let's start with our domain for this graph. So here we can see that with these arrows, it's showing that it is going up forever to the left and right, but you can also see that it is going over a little bit to the right and left. So although it's going up much faster, it will keep extending to the left and right infinitely. So here our domain is all real numbers. So negative infinity to positive infinity in interval notation. And then we could say x such that x is all real numbers for a set builder notation. Now for our range, we can see that our range does have a restriction. It does hit a low point at negative 4, and then it's everything above. So this will go from negative 4 to infinity, and because our graph goes through the coordinate 0, negative 4 is part of our range. Or if we were using set builders, it'd be y such that y is greater than or equal to negative 4. So make sure you're using the correct variable when you are using that set builders notation. All right, let's try another one together. So kind of similar to the last example, you could see that these arrows denote that it is going down forever, but it's also going slightly to the right and left forever. So for our x values, it will eventually hit all real numbers to the left and right. So negative infinity to positive infinity, or x such that x is represented by all real numbers. And then for our range, which again is the y values, we can see that it's everything below and including positive 5. So remember, for interval notation, we always go low to high. So negative infinity to 5, and I used a bracket because 5 is part of our range. Or we could say y such that y is less than or equal to 5. And notice that, again, when we write this vertical line, we read it as such that, y such that. All right, let's try one more together. So here you see that we actually have what's called a piecewise function. So it's kind of split up into different pieces, and some of our coordinates you'll notice are open and some are closed. So let's start with our domain. So as long as the x value exists somewhere on our graph, we will include it in our domain. For example, I know that this is an open coordinate here at x equals -2, but since it's a closed coordinate here, -2 is part of our domain somewhere, so we will include it. Same here for +4. I know this is open, but here it is closed, so it exists somewhere. Now, if you look at -6, this is a closed coordinate, so -6 will be our lowest x value. But if you look to the right, our highest x value is at 8, but that coordinate is open, so 8 will not be included in our domain. For set builders, we can say x such that -6 is less than or equal to x, which is less than 8. So make sure you're not including 8 in your domain. Now for our range, let's take a look. So again, as long as the y value exists somewhere, we will include it. So here around y equals 5, I know it's not included here, but it is included somewhere else. Here at 6, it's not included here, but it exists somewhere. So really our range is going to be everywhere between, I'll just estimate that this is -7 all the way up to 9. So again, as long as it exists somewhere, we will include it. So our low value, it looks to be -7. Our high value looks to be +9. And for set builders, we'll say y such that -7 is less than or equal to y is less than or equal to 9. So make sure both -7 and 9 are included in your range. All right, so now I have one for you to try on your own. So please pause your video and then you can hit play when you're ready to check. All right, go ahead and check here. I know that there's all these different pieces to this graph and there's some open coordinates, but really you can see that everything above 0 is included for our range, and 0 is included. It's included somewhere, and you can see that our graph actually goes to the right and left infinitely, which is why our domain is actually all real numbers. Every x value is included somewhere on our graph. All right, so the next thing we're going to talk about is what's called linearity. So a linear function, which is one of the first types of functions we're going to be working with, is a function which has no variable, in which no variable is raised to a power other than 1. Okay, so again, no variable is raised to a power other than 1, so there shouldn't be anything being squared, there shouldn't be any square roots or anything like that. All linear functions can be written in the form of y equals mx plus b, where m and b are real numbers. So that's one way to check to see if something is linear, if you can rewrite it in this form. Graphically, we know that an equation is linear if the graph makes a straight line, or you could say has a constant slope. Okay, so let's look at these three equations and see if we can determine whether or not they are linear. So this first equation, I want to remind you that f of x is completely interchangeable with y. We can actually just divide each of our terms by 3, and you can see that it can be written in this form, meaning that it is linear. You can also see that both x and y are just raised to the power of 1, which is another way to determine that it is linear for that first equation. Now, if you look at this next equation, right off the bat, you'll see that x is being cubed, being raised to the power of 3, so we can see that this is a nonlinear function. And then for this last equation, I know that maybe you're thinking, oh, this is not linear because I don't even see an x, but remember, m and b can be any real number, and 0 is a real number. So if you just have y equals 9, it actually just makes a horizontal line at the value y equals 9, and this is considered to be a linear function. It has a specific name. Technically, this is called a constant function, which would be a type of linear function, but this does make a straight line. The slope is just 0, and again, this will be considered a linear function. Another really important characteristic of functions will be the intercept. So both the x and the y intercepts, which is just the x-intercept is just the x-coordinate where the graph crosses the x-axis. Again, it is possible for functions to have more than one x-intercept. Not linear functions, but other types of functions can. And then the y-intercept is simply the y-coordinate of a point where the graph crosses the y-axis. And to maintain the property of functions should never have more than one y-intercept, or by definition, they wouldn't be a function anymore. So here we're going to practice finding our x and y intercepts algebraically. So to find, let's start with our x-intercept. If our x-intercept is where the graph crosses our x-axis, that is always going to occur when y equals 0. So to find an x-intercept, we set y equal to 0, and we see what the x value is. So I'm going to substitute y with 0, and I'm just going to solve for x. So we can see that x is equal to -3. That's our x-intercept. And then we could write it as a coordinate like this. So it'll be -3, 0. And our y-intercept, well, if it's where it crosses the y-axis, that will always occur when x is 0. So we're going to set x equal to 0. So we'll substitute into our equation, and then we're just going to solve for y. So y equals 9/2. So this would be our y-intercept. So 0, 9/2 would be the full coordinate. And you will notice that kind of throughout the year, I will be using mostly fractions rather than decimals, which I would also like you to do. Always make sure they're simplified. And notice here, we are going to be using improper fractions. So we will just keep this as 9/2 rather than 4 1/2. So please get in the habit of being comfortable with improper fractions and just always make sure they are simplified. All right, the next characteristic we're going to talk about is symmetry. So some graphs or some functions do display different types of symmetry, but it's also very possible for a graph to show no symmetry at all. So it can be neither of these things, but there are two main types of symmetry we are going to be looking for. The first one is called line symmetry, and that's when your graph is reflected over a vertical line so that the two halves are equal. So if you look in this at this parabola, which is a quadratic function, if you draw this vertical line here, you can see that the graph to the right is completely identical to what's to the left of that vertical line. Or if you folded your paper on this vertical line, the graphs would meet up. So this is called line symmetry, and we could even define the line that it is symmetrical over. And then if you look at this next graph, this graph displays what's called point symmetry. So that's when a graph is rotated 180 degrees, which is half of a circle, about a point to map itself onto, maps onto itself. So you can see here that if you took this half of our graph and we kind of rotated it about, in this case, our point is the origin. If we rotated about the origin, it would map perfectly onto this half of the graph. Another way you can kind of check for this graphically, if you pick any point on your graph and you draw a line through that point and your point of rotation, which again in this graph is the origin, you can see that if you continued that line, the other point that it goes through would be the opposite of those y values and is the same distance to your point of rotation. So we can kind of use that to help us determine where that point of rotation would be. So these are the two types of symmetry we're going to be looking for. And again, it's very possible for a graph to not display either of these types of symmetry, and that's fine as well. Okay, so here we're looking at three different graphs and trying to identify if a type of symmetry exists. So here we actually have a linear equation, and actually all linear equations actually they display point symmetry, and actually the point of rotation could be any point on the graph. So all of this graph, any linear equation does have point symmetry. and the point of rotation could be, I'll say, about any point on the graph. And again, I could take this point, and you could see maybe if I took this point right here and I rotated it 180 degrees, it would land right here. And we could take any point on the graph as the point of rotation and pick any point to the left or right and rotate it 180 degrees, and it should still fall on your line. Now, if you look at example B, this portion of our graph looks like it does have that rotational symmetry. However, you can see that then we have this portion of the graph, so there is no rotational symmetry, and we could also see that there's no line symmetry because it's not reflected exactly left to right. So this one would be neither. And then if you look at this third example here, we can see that there is a vertical line that kind of reflects our graph. That vertical line would be right here. I know the scaling on this graph is a little bit strange, but each tick mark should be 1. I think some of these points just got kind of shifted over. So we would call this line symmetry. And we would say about, and we're going to define this vertical line, and this is x equals -3. So it's about the line x equals -3. And you could, again, if you folded your paper on this line, we would see that both halves of our graph would match perfectly. And there you have it. The last thing we're going to talk about today is yet another way that we can describe some functions, and that's by either classifying them as even functions or odd functions. Now, it's also very possible for functions to be neither even nor odd, but if you can classify them, as we kind of move forward throughout the year, you'll see why this will be useful to us as we learn to graph and we learn about different features of our functions. So first, an even function. There is an algebraic test for this, which is kind of the mathematical definition of an even function. So here's the algebraic test. It says f of -x equals f of x. So what does this mean? Well, you can see what it means is if you plug in the opposite x value, so if you substitute the opposite x value, and notice I'm not using the word negative, I'm just using opposite. So we have x and -x, which would be opposites. But plugging in or substituting the opposite x value actually gives you the same result as if you plugged in f of x. So it results in the same y value. So if you substitute the opposite x value, you get the same y value. That would be like if you plugged in -5 and the output was +2, and if you plugged in +5 and the output was also +2, we could say that that is an even function, as long as that holds true for any x value. So opposite x values give you the same y value. Graphically, a graph that is, or a function that is considered to be even will always be reflected over the y-axis. So if you notice that it has line symmetry about the y-axis, this would be considered an even function. So you could either look at the graph and determine, or you can do the algebraic test. Now, for an odd function, the algebraic test or the mathematical definition is that f of -x equals -f of x. So what in the world does this mean? This means if you substitute the opposite x value, again, if you substitute the opposite x value, you get, or the output is, the opposite y value. So plugging in the opposite x value gives you the opposite y value. You get the opposite y value. So graphically, you can tell if a function is odd if it has point symmetry about the origin. meaning it is rotated 180 degrees about the origin, kind of like that first kind of cubic function that we looked at. So it is going to be useful for us to be able to either look at an equation and do an algebraic test, or look at a picture of a graph and determine graphically if we have an even or odd function, or maybe it is neither. So we're going to give a couple of these a try. So here we're going to do the algebraic test for these. So anytime you're trying to test, what we do is we plug in negative x, or the opposite x, and then we're actually going to evaluate this in our function and see what happens. So here we'd have negative 2 times negative x to the power of 5 plus 3 times negative x to the power of 3 minus 7 times negative x. Now if we simplify this, we know that if you have a negative value being raised to an odd power, the result is a negative. So this will actually give you negative x to the 5th. So if you multiply it by negative 2, this actually becomes positive 2x to the 5th. Same idea here. If you have negative x cubed, that is negative 1 times x cubed. So that turns this entire term into negative 3x cubed. And here we know negative 7 times negative x gives us positive x. So what you'll notice is when we plugged in the opposite x value, you'll notice that our entire, our entire function was made opposite. So really what's happening here is that f of negative x gave us negative f of x. Plugging in the opposite x value gave us a completely opposite y value. So again, every single term in my function was made opposite, meaning it changed from either negative to positive or from positive to negative. So because that is happening, this function is classified as odd. Now if you look at part B, let's do that same algebraic test. We have 0.5 times negative x squared plus 11. So let's simplify that. We know that if we square a negative, it will always result in a positive. So this first term actually just stays exactly the same. Again, squaring it just essentially negates that negative. And then 11 is a constant, right? There's no variable. It will never change. 11 will always be 11 no matter what we're substituting into our function. So when we substituted the opposite x value, we actually got the exact same y value. So here, this is f of negative x is equal to just the original function, f of x. And this is the definition of an even function. Now, if you look at part C, let's do our algebraic test. So I'm substituting negative x. This first term, we're cubing it, so it turns the entire term negative. Here this will become minus 3x, but our constant will never change. So here our first term became opposite, our second term became opposite, but our third term did not. So here we would not say, so f of negative x is not equal to negative f of x. Not everything became opposite, but we would also say that it is not equal to the original function. It is not exactly the same. So if it's not exactly the same and it's not exactly opposite, this is a case where we would say that it is neither even nor odd. So there is kind of a little cheat that you could do when you're looking at an equation. If you're looking at a function and you notice that all of the variables, every single term has a variable with an odd exponent, that function will be odd. And if all of the terms have a variable with an even exponent or no variable, meaning it's a constant, if everything is even or constant, the function is even. Now, if you have a mixture of even and odd exponents or odd exponents with a constant, that's when it's going to be neither. So that's kind of the shortcut, but we would still want you to be comfortable with this algebraic substitution to determine if something is even or odd. All right, that is all for today's video. Thank you so much for watching.